This video is going to talk about the multiplicative model, which is a very useful model that gets used in a lot of different fields. So the multiplicative model has a multiplicative form. So y is going to be the product of some scaling coefficient beta naught times x1 to the beta 1 times, say, x2 to the beta 2 times some errors. So it looks just like the usual multiple regression model, except that all the plus signs have been replaced by multiplication signs. And the other thing that's happened is that your coefficients get moved up into the exponents. So these slope coefficients are in the exponents. Now, let's take logs of both sides of this model. Now, once you take logs, you get a function that's very attractive. So you just have the log of y is going to be the log of some, the scaling constant beta naught. Then beta 1 times the log of x, beta 2 times the log of x2, and so forth. So this looks really like just the regular multiple regression model, except that all my variables are logged ahead of time. So in other words, if I were to regress the log of y on the log of x1 and the log of x2, I would get exactly this model. Now, there's a few differences that should be highlighted. One is the error structure. So here we're assuming that we've got these errors also have been logged and that they're additive now in this model. And it turns out that that's often a very reasonable assumption to make. A few more properties of this model that you'll need to know. When it comes to making predictions, you have to do something that's a little bit more complicated than you'd expect. So you might expect we'll just exponentiate the predicted values, and that would be what you'd get if you exponentiated this part. Turns out that you need to add a correction, and this correction accounts for the fact that when you unlog a distribution, the extreme tail is going to pull the mean out. It's going to be pulled out by this standard error of the regression over 2. Okay, sorry, standard error of the regression squared over 2. The coefficient of variation is going to be this standard error of the estimate squared minus 1 square rooted. The interpretation of the parameters are also a little bit different. So let's go back to the original model. So here's the model. To keep things a little bit simpler, let's only have one predictor at this point. And let's just take a look at what this is. So if beta 1 were equal to 1, okay, so in other words, if this exponent were equal to 1, what would we have? Well, then we would have y is just proportional to x. So y is just going to be some multiplicative constant times x, which means that we have a line that passes through the origin. However, when beta 1 is not equal to 1, we're going to get one of two shapes. So if beta 1 is between 0 and 1, then y is going to, the change in y will decrease as x gets bigger, so you get diminishing returns. If beta 1 is greater than 1, then you get increasing returns. Now, so often we want to compare the coefficient beta 1 with the value 1 instead of 0, as we often do. So the value 1 means proportional. Values less than 1, greater than 0 would be decreasing returns to scale, and values greater than 1 are increasing returns to scale. In economics, these beta coefficients have a special interpretation called elasticity. So what is an elasticity? Well, elasticity is just the expected percentage change in y with of a 1% change in x. So let's go directly from the definition here. It's the expected percentage change in y. So what is the change in y relative to the y value for a corresponding percentage change in x, relative to the x value? So I've worked out the derivatives for you up above, and so what you'll see is that sure enough, this percentage change in y relative to the percentage change in x works out to be exactly this regression coefficient. At this point, I want to go over a nice problem that illustrates how to use these multiplicative models. So in this example, we have a data set, and I've already loaded that data set. It's a data set called business failure, bizfail.csv. You can get it from Blackboard. What we have are the number of business failures in each state plus the District of Columbia, as well as the population in thousands for each of those states. And you also have the state name. So part 1 asks us to make a scatter plot of business failure against population and to superimpose a regression line. So let's go do that. You'll notice that the variables are called failures and population. So let's first estimate the regression line. So failures as a function of population, and then let's plot bizfail dollar. We want to put population on the x-axis, and then bizfail dollar failures. And so here's that scatter plot. And the first thing we notice about this scatter plot is that most of the data are off in this corner. It appears that we have some heteroscedasticity. So notice how there's very little variation in failures for low values of population, but as population increases, the variance increases. The other thing to note is that there's an outlier way up here in the corner. So this is not a very good situation for regression. If we do an A-B line of fit, you're going to see a pretty poor fit. So the regression line really doesn't pass through the middle of the data. What's happening is this one value up here is pulling the whole line up. So if we wanted to find out what that value is, we could, I'm going to go over to re-edit this command. There's a command called identify. So identify, and we can put in bizfail dollar, and I think it's state. And now I can go over to this plot, and we have a little plus sign. And if I click on this point, you're going to see it's actually California. And this is New York. This is probably Texas. Let's try, yeah, that's Texas. And that's Florida. And to get out of this, you just hit escape, and you're out. Okay, so we've got a problem with California that's bringing up the entire regression line. Let's now go back to the course packet and do part 2. So I guess the conclusion to question 1 is the linear model doesn't hold because of an outlier, because of heteroscedasticity. So it's we need to do something different. So make a scatter plot of the log of business failure against the log of population. Superimpose a regression line. Does the linear model hold better? So this is really just a multiplicative model. So I'm going to go re-edit this command, and we're going to make the log of business failure dollar population and the log of failures. And if I go look at the scatter plot, this looks much more like a textbook scatter plot for linear regression. So the logs have cleaned up all these issues. California is no longer an outlier. The variance is no longer very heteroscedastic. it looks pretty constant. So the log-log model has cleaned this up. Now we're to fit a regression model, so let's go bring back that regression command. Let's call this fit2, and we can just add the log function within the LM call. So let's have the log of failures regressed on the log of population. And if I do an AB line fit2, we see that we have a very good fit. We could also examine residuals. So if we do a plot of fit2, what you'll see is that the residuals look pretty good now, as opposed to before. If we do a plot of fit, this was the regression where we had unlogged data. You'll see that you've got an outlier, pardon me. All of the residuals are positive for small values of population, then they're mostly negative for larger values. So that indicates this lack of fit. So it looks like the log model has really improved this. So regress the log of failures and the log of population, state the estimated regression equation. So if we do a summary on fit2, we'll get to see that estimated regression equation. So the way I would state this is that the log of failures is right here. So the log of failures equals the minus 1.91 plus 1.07 times the log of population. Test at the 5% level to see whether there's a significant relationship between the log of failures and population. So there's a couple ways that we can do this. Either the overall test of significance is one way, or we get the exact same p-value if we use the slope for log population. In either case, that slope has a p-value that is tiny, or the overall regression has the exact same p-value, which is 10 to the minus 16th. So we'd reject the null hypothesis that the coefficient is 0, meaning that there would be no relationship. Question 5. Test whether the population slope for logs is significantly different from 1 or not. What does this tell you? All right, so remember what a value 1 tells us. 1 means that failures are proportional to population. So let's find out if we can conclude that they're proportional or not proportional. How do we do this? Well, there's really two ways to do this. One is with the confidence interval approach. One is with the p-value approach. So if we type conf int of fit2, we're going to get a confidence interval for our regression slopes. What you'll notice is the value 1 is contained in the confidence interval for log population, so we cannot reject the null hypothesis that the slope is 1. It's entirely plausible that the slope equals 1 and that failures are proportional to population. The other approach would be to do find a p-value for this. So how would we find the p-value? Well, we're going to take the observed statistic, which is 1.07185, subtract from that the mean. So the mean under the null hypothesis that this slope is 1 is 1. Now we need to divide that by the standard error, so 0.05732, and we get a t-statistic of 1.25. Now if I want to find the tail probability of this, I can use a normal distribution, I guess. So 1 minus p norm tells us that there's about 10% in the right tail. If I multiply that by 2, my p-value is going to be about 21%. So why don't I do that? Here would be your two-sided p-value. So 2 times that whole quantity is about 21%. So I can't reject the null hypothesis that the slope is 1. So I get the exact same conclusion. In this case, I think using the confidence interval approach is a bit easier. So here's one of those instances where R doesn't hand you a p-value and you want to use the confidence interval. Illinois had 2,094 failures and a population of 11,000 something. Find the predicted log failure for Illinois. So let's go back to R, and we can do this a number of ways. I suppose the simplest way would be to just look at the fitted values. So if we look at fit2, $fitted values, we have all these fitted values. So the question is, which of these values is Illinois? So Illinois is observation 14. And so if I were to take fitted values sub 14, I get the estimated value for Illinois. Now another way to do that, if you're curious about where that came from, it's really minus 1.91165. So that's my intercept. And then I'll copy this down. So plus the log of population, so 11,697 times the slope. And so you'll see that we get exactly what R got. So that's where R is getting that. And I'd say that's the answer to question 6. Identify unlogged failures and identify Illinois in your scatter plot. We already did that. And there's a couple other things that we might want to do if we wanted to compute unlogged predicted values. So let's go back and look at the course packet for a second. If I want to make an estimate of the actual failures in Illinois, I'm going to take the predicted value. So this is that 8 point whatever thing that I just computed. And I have to add to that the mean squared error over 2. So where do I get that? How am I going to do this? Well, let's go back and take my fitted value. So that's 8.12. And the mean squared error is going to be given by, this is the standard error of the estimate. So if I take this value and square it, I got to divide that by 2. So all I'm doing is I'm taking, S sub epsilon is that 0.411 thing. We're going to square it and divide by 2. Now I need to exponentiate this whole thing. And so 3,700 is my predicted value, whereas the observed value, BizFail sub 14, was actually substantially lower. So Illinois had fewer failures than we would expect under this model.